Gravitational potential energy. A barbell of mass m is lifted vertically a distance h by an external force F external at a constant velocity. How much work does that external force do on the barbell? We start with the free body diagram. The external force is in the up direction, mg is in the down direction. We then use Newton's second law, F equals ma, and we sum the forces up. F external is up, so that's positive. Mg is down, so that's negative. The acceleration is 0. Why? Right here, we said we're lifting it at a constant velocity. So we solve that and we find F external is equal to mg. Now we come down to our work equation. Work is F times d parallel. Well, we sub in F external for the force, and we sub in h for the distance moved. Now they are parallel, so we just write F external times h, and we're looking for the work external, so we throw a subscript on there. But what's F external equal to? Right over here, and you can see the red arrow hopefully going down. We substitute that in for x external, and then, F external, and then we find the work done by the external force is mgh. Now let's invoke the work energy equation. Initial energy plus work equals final. Our barbell had no energy to begin with, so that means E0 is 0. So its final energy must be the work that was done to it. So we have work is equal to E final. We showed on the previous slide that the external force did an amount of work equal to mgh to lift the barbell. So we substitute mgh in for work, and we have mgh equals E final. The name for this form of energy is gravitational potential energy. So GPE equals mgh. One important thing to note is that while changes in gravitational potential energy are important, their absolute value is not, and we'll show you on the next slide how we defend that statement. You can define any height to be the 0 for height, and therefore the 0 for GPE. But whichever height you choose to call 0, changes in height will result in changes of GPE. For example, the floor level over here can be considered 0 energy, or the ladder level can be considered 0 energy. So when we find the mgh here, that will equal the mgh here. We're just looking for the change in energy there, and since they both have the same height, you'll have the same change in GPE for each example. We'll show how we use the GPE equals mgh equation now. We're going to take a 3 kilogram object, and it's going to move from 5 meters above the ground to 8 meters above the ground. What is the change in GPE? We start with our givens. Here's the mass of the object, here's the initial height, and here's the final height. So we've modified the equation a bit to be just not GPE equals mgh, but we're going to find the change in GPE between two different heights. So it'll be mg h final minus h0, and it's always final minus initial. We then substitute in our givens, and we find that the change in GPE was 88 joules. It increased. Now we'll have an object falling, getting closer to the ground. We have a 2.4 kilogram toy falling from 2 meters to 1 meters. What is its change in GPE? We have our givens here. Here's the mass, here's the initial height, final height. Our delta GPE equation, and again, always final minus initial heights, we plug in our values, and this time we have 1 meter minus 2 meters, so we're going to get a negative value. And yes, we do. The GPE of the system decreased by 24.5 joules.